Today we're going to talk a little bit about adding and subtracting with radical expressions. Adding and subtracting with radical expressions is a lot like adding and subtracting monomials or variable expressions. So I actually want to jump right in with our first example to show you what I mean by that. So right above this expression, so you can see that there's a couple of different radicands. So there's a couple of square root of 3's, and then there's a couple of square root of 7's. So I'm going to replace those radicals with variables for just a minute to help you see the connection between working with a radical expression and what you already know about working with monomials, regular expressions. So I'm going to change my square root of 3's into x's. So I'm going to turn this into a 4x and a 6x. And I'm going to change my square root of 7's into y. So 3y minus and 5y. So if I gave you this, 4x plus 3y minus 6x plus 5y, you would be pretty quick to say, okay, those get combined and the y's get combined. So working with radical expressions is the same idea. And when you combine these, so 4x minus 6x is negative 2x, so the variable part stays the same. So those are things we know about working with expressions because we've been doing that for a while now. We could take the same idea and use it working with radicals, but your x's and your y's are now the radicands. So I can combine things that have the same radicand, and then just like how you would combine like terms with variables, the radicand stays the same. So kind of like how 4x minus 6x is 2x. It's still got that same variable in there. So it's still at the same radicand. So it's basically the same idea as what you've been doing for a while now with combining like terms and variables, but now your variable has turned into a radicand. So I can take the 4 square root 3 minus 6 square root 3, and I could put those together just like a 4x minus 6x. So it would be negative 2 times the square root of 3, just like how the x would stay the same, the radicand stays the same. And then I can also take the 3 square root of 7 and the 5 square root of 7 because those have the same radicand. That basically means they're like terms in the radical world. So I could put those together, and that is a positive or plus 8 times the square root of 7. So I could take this 4 times the square root of 3 plus 3 times the square root of 7 minus 6 times the square root of 3 plus 5 times the square root of 7, and I could simplify it down into this. So negative 2 times the square root of 3 plus 8 times the square root of 7. And that's as far as I can go because square root of 3 and square root of 7, those are different radicands. So that would be kind of like having an x and a y. Those aren't like terms. I can't put them together. So adding and subtracting with radicals is a lot like simplifying expressions and combining like terms. Your radicands are kind of like your variables. So you would treat it the same way as you would treat variable. So that is what the statement up here is kind of telling you. So radical expressions with the same radicand be combined using addition and subtraction. Adding or subtracting, the radicands be combined. The radicand does not change. So basically, that's telling you, hey, I can combine like terms with radical expressions. Now, there is one thing to be aware of. When you're adding or subtracting, always simplify first because you might have something you can combine and just not realize you can combine it because you won't see it until you simplify it. So an example of that is this second problem that we've got here. So we've got a square root of 24 minus square root of 54 plus square root of 96. Well, each of those can be simplified. So we're going to go through and we are going to individually simplify these so that we can see what they actually are. So square root of 24 breaks down into 2 times 2 times 3. And then times 2 again. Sorry, I forgot a times 2 in there. So 2 times 2 times 2 times 3. That means that I've got a perfect square I can pull out. So, and then those are going to be the leftovers that are going to stay. So 2 times 3 times 2, square root of 6. Now I've got to go through and I've got to do that with my other problems as well. So square root of 54, if I break that all down, was 2 times 3 times 3 times 3. So I can pull out a perfect square there, and then those leftovers stay, so I end up with 3 times the square root of 6. And we can see that we already have some radicands that are the same. So that means when we come back to this, we can put those back together. But now we've got our third one, the square root of 96. So we have 3 different things in here. So let's go through and simplify each of those so that we have the full picture of what we can put together. And then one more, 2 times 3. So this one I've got a couple of pairs of things I could pull out. So I could pull out 2 2s. So if I pull out 2 2s, I'm going to end up with 2 times 2 sitting on the outside, which would be 4. And then my leftovers are square root of 6. So I could take the square root of 24 minus the square root of 54 plus the square root of 96, and I can rewrite it as 2 times the square root of 6 minus 3 times the square root of 6 plus 4 times the square root of 6. So it's the same expressions, just rewritten. And you can see with these all simplified that, hey, they all have the same radicand. So these are basically like terms. So I could put them together just like if that square root of 6 was an x. So it would be like saying 2x minus 3x plus 4x. So I can combine my coefficients, or my constant terms in this case. So 2 minus 3 is negative 1 plus 4 is 3. And so they're all square root of 6, it stays square root of 6. So that would be my final answer, would be 3 times the square root of 6. So that whole thing boils down into 3 times the square root of 6. So always simplify first. So one more example. So this one you might look at it and go, well, wait a minute, there's only one radical in here. But I want you to remember that rule and even write it above here just to remind you. This would be a good thing to put in your notes. Always simplify first. So if we follow the always simplify first rule, this expression is not simplified because we can't have a fraction in the radicand. So that means we need to do a little bit of work with this guy to get it rewritten. So I could break it apart into square root of 1 over the square root of 5, but now I can't have a radical in the denominator. So we have to use our rationalizing the denominator trick from last week, where we multiply this, the top and the bottom, so that I'm really multiplying by 1 by the square root of 5. So that turns this into the square root of 5 over square root of 5 times square root of 5 is going to be square root of 25, which is just 5. So now I've got this. So you might be thinking, well, okay, wait a minute, those aren't like terms. Now you do need to remember one thing. If you have fractions, we know that you can add or subtract fractions if we make a common denominator. So if you have fractions in the mix, you should always make a common denominator and then go ahead and do your adding or subtracting with your common denominator. So I can make a common denominator of fifths, and I can rewrite my 5 as 25 fifths. And then now that these have the same denominator, I can go ahead and subtract. So my denominator is going to be 5. And you might be thinking, well, wait a minute, I can't actually do the square root of 5 minus 25. So that would be my numerator, but I would just have to leave it as the square root of 5 minus 25. But when you can, it's a good idea to get your parts and try and get them all under one denominator so that you can combine it all together. So this would be my simplified answer. So your simplified answer should never have multiple different fractions in it, because you can combine everything into one giant fraction by putting it all over a common denominator. So always go for a common denominator when you're adding or subtracting. So to summarize this, basically what we're doing is if we have two things that have the same radicand, then I want to keep that radicand. So whatever my radicand is, it stays the same. But the number out in front of that is going to be the combination, the plus or minus, because you could add or you could subtract. So add or subtract, whatever you need to do, the terms. So it would look something like this. Just take your terms, combine them, and the radicand stays the same. So that's adding and subtracting. So operating with radicals. You can add or subtract radicals if they have the same radicand. Kind of like with fractions. So fractions are like terms. So like with fractions, you can add or subtract fractions if they have the same denominator, if they have something in common. But when you're multiplying, we don't have to worry about that. We can multiply whatever the numbers are. So that same sort of thing is also true with radicals. So radicals do not have to have the same radicand in order to multiply them. If I'm going to multiply them, I can just go ahead and multiply it all together. So like this first problem, 2 times the square root of 6 plus 7 times the square root of 3. I can rearrange this problem because remember, we're really multiplying. So we've really got like 4 separate pieces. 2 times the square root of 6 is the second piece, times 7 is the third piece, times square root of 3 is the fourth piece. So you really have to think of it as I actually have 4 different things I'm multiplying. And we can multiply in any order we want. So I'm going to rearrange this multiplying. And I'm going to say 2 times 7 times the square root of 6 times the square root of 3. Well, we can do 2 times 7. That's going to give us 14. And we have our product property of square root. So our product property says that we could take a radicand and we could split it apart into 2 different things we're multiplying. But we could also take that and we could put it back together. So I can put these same things back together into the same radicand, 6 times 3. And if I clean that all up, well, actually, before I even clean it up, I need to think about simplifying. So I can put the 6 times 3 together, but the 6 I can also break down. So if I break that down, now that I've got these 2 things combined under the same radicand, I need to look and see, okay, now that I put pieces together, do putting those pieces together make any perfect squares? And in this case, it does, because when I put the 6 together with the 3, 6 can be broken down into 2 times 3. When it combines with the other 3, it makes a perfect square that I can pull out. So that means I can pull out a 3 and make this into 14 times 3 times the square root of 2. And then 14 times 3, I can go ahead and multiply. So that's 42 times the square root of 2. So when you're multiplying, you don't need to worry about a common radicand. You can just multiply the coefficients or the numbers outside the radical symbol and go ahead and multiply the radicands together underneath and then look and see once you've combined things, does combining thing make any perfect squares that you can pull out to simplify? So same idea here, and this you're working with a little bit, and we talked about conjugates last week, but you could do some distributive property work with radicals, and one place where you would do that is if you're working with conjugates, which we were. So this is just a reminder that when you do that, you can use all these things we were talking about potentially adding or subtracting radicals so the radicands are the same, and this idea of multiplying where you just multiply the coefficients or the numbers and multiply the radicands. So if I do some distributive property with this, I'm going to start by doing some multiplying. So I'm going to have to do 5 times the square root of 3 times 3 times the square root of 2. So I can multiply the numbers outside. 5 times 3 is 15. I can multiply the radicands. 3 and 2 makes 6, and I'm not going to get any perfect squares out of that, so that really is 15 times the square root of 6. And then I can do the same thing with the second part. So minus 5, and in this case, I'm going to end up doing 3 square root of 3 times 3. Well, that makes a perfect square. So 15 times the square root of 6. Square root of 3 times 3 is 9. Square root of 9 is 3, so that's going to turn into 5 times 3, which is 15. Now, don't be fooled by this. They both have a 15, but they do not have the same radicand. This has a radicand of 6. This has no radicand. So that means they're not like terms because they do not have the same radicand. So that means that is as far as I can go with this. So 15 times the square root of 6 minus 15 would be a simplified version of that. Similar to working with expressions, we know working from expressions that when something's simplified, we don't want it to have parentheses. So that's also true with radical expressions. So if you have some parentheses and you can do some distributive property like this last example to get rid of the parentheses, then you should go ahead and do that. So summarizing this idea of multiplying. we can take the coefficients, whatever they are, and go ahead and multiply those together. And then we could take the radicands and go ahead and multiply them together to make a combined radicand. And then, of course, look and see if you can simplify once you put the parts together. So to add or subtract, we need to have radicands that are the same, kind of like terms, or common denominator with fractions. To multiply, we don't have to have the same radicand. We can just put it all together. So what you're going to work with today are some problems where you're going to be practicing adding and subtracting and multiplying with radical expressions using these examples and these rules that we just finished talking about.